In the 1960s, Jeffrey Chew, a renowned and influential physicist at the University of California, Berkeley, proposed a revolutionary and daring framework for understanding the universe that he called bootstrap philosophy. This period is known for the discovery of a large number of subatomic particles, leading physicists to grapple with categorizing them into elementary particles and composites. However, Chew's radical perspective challenged this reductionist paradigm that had dominated scientific thought since Democritus. Reductionism suggests that everything in the universe can be understood by breaking it down into its most basic, indivisible, and self-explanatory components. In contrast to this view, Chew argued that the laws of the universe could be derived from the principle of self-consistency alone, without resorting to identifying the fundamental building blocks. He argued that all particles are simultaneously composite and elementary. This concept forms the basis of bootstrap philosophy. He proposed that each particle is composed of other particles, and that these components are linked together through interactions that involve the exchange of the original particle, creating a self-consistent feedback loop. In other words, particles are interdependent and self-referential, each holistically generating the properties of the others. Chew's approach differed significantly from traditional physics in that it did not provide a detailed procedural manual. Instead, it relied on applying general principles and consistency conditions to deduce the properties of particles and hence the laws of nature. This method achieved early success when Chew's students used it to estimate the mass of the RHO meson. The RHO meson, composed of pions linked together through the exchange of RHO mesons, exemplified the bootstrap principle and garnered significant interest and support from the scientific community. However, the bootstrap philosophy faced limitations. The prediction of the Rho meson's mass proved to be an exceptional case rather than a generalizable result. A competing theory known as quantum chromodynamics, QCD, proposed that protons and neutrons are composed of more fundamental entities called quarks. QCD provided a more accurate and experimentally consistent framework for understanding particle interactions and became the cornerstone of the Standard Model of particle physics. The Standard Model, which included QCD, was able to explain a wide range of experimental data and provided a more robust framework for understanding the fundamental forces and particles. Despite the initial enthusiasm and innovative nature of Chew's bootstrap philosophy, it ultimately failed to compete with the predictive power and experimental success of the quark model and QCD. The properties of individual quarks appear to be arbitrary and dependent on the specific conditions of the universe. In alternative universes, these properties can vary, suggesting that the particle configurations we observe do not represent a single consistent framework for nature. Instead, an infinite number of potential particles can be envisioned, each interacting in various spatial dimensions defined by a unique quantum field theory. For decades, the bootstrap method was largely sidelined in physicists' toolkits. However, recent developments have revitalized the field as new bootstrap techniques emerge to address a wide range of theoretical challenges. While traditional consistency conditions are inadequate for solving the complex dynamics of nuclear particles, the bootstrap approach is proving effective in understanding more symmetric and idealized theories. Viewed by experts as guidelines or building blocks, these theories map out the vast landscape of possible quantum field theories. Despite the unexpected nature of their results, these physicists reveal that the set of all quantum field theories forms a unique mathematical structure. This structure, consistent with Chew's original bootstrap concept, is self-determining and intrinsically understandable. This phenomenon clarifies general features of quantum gravity theories and offers insights into the quantum origins of gravity and the nature of space-time. Technically, the bootstrap method calculates correlation functions, which encode the relationships between particles described by a quantum field theory. For example, in a piece of iron, correlation functions express the probability that the iron atoms will magnetically align in the same direction relative to their distance. A two-point correlation function provides the probability of alignment between two atoms. A three-point correlation function extends this to three atoms, and so on. These functions contain extensive information about the iron sample, but they often make them difficult to calculate because they involve an infinite number of terms with unknown exponents and coefficients. The bootstrap approach aims to constrain these terms to solve for the unknown variables. Although this usually makes limited progress, in special cases the bootstrap method can solve these equations exactly, as theoretical physicist Alexander Polyakov began to show in the 1970s. Polyakov and his team discovered that when brought to their critical points during phase transitions, very different materials exhibit the same behaviors characterized by a small set of universal numbers. For example, when the iron is heated to its critical temperature and loses its magnetization, the correlations between its atoms can be described by the same critical exponents that apply to water at the critical point where the liquid and vapor phases meet. These critical exponents are universal, independent of the specific microscopic details of the materials in question, suggesting a fundamental principle shared among systems in the same universality class. The ultimate goal, as Polyakov described it, was to calculate these critical exponents from fundamental principles. This quest resulted in the fact that materials have common symmetries at their critical points. In particular, a set of geometric transformations known as conformal symmetries, of which scale symmetry is the most important. Scale symmetry means that at the critical point, the system looks the same at any level of magnification. For example, zooming in or out at the critical point of iron reveals a repeating pattern of patches of atoms aligned in alternating directions, continuing at all scales. This property shows that in conformal systems there are no absolute concepts of near and far, because any local perturbation, such as flipping an iron atom, has a global effect. Polyakov explained that this causes the entire system to behave like a highly correlated environment. However, the macroscopic world we experience is not conformal. The existence of elementary particles such as quarks breaks scale symmetry by introducing fundamental mass and distance scales into nature. This symmetry breaking creates a hierarchical structure in the universe, where planets are much larger and more massive than humans, humans are larger than atoms, and atoms dwarf quarks. These introduced scales break scale symmetry that could simplify the description of interactions, thus making correlation functions with arbitrary variables difficult. While Chu's approach aimed to derive particle properties through self-consistent feedback loops without fundamental building blocks, the hierarchical nature of reality, with its arbitrary masses and lengths, introduced complexities that the bootstrap method could not easily handle. In this context, conformal systems governed by conformal field theories, CFTs, exhibit uniformity on all scales. This property makes them particularly suitable for a bootstrap approach, as discovered by Alexander Polyakov. Alexander Belявin, Polyakov, and Alexander Zamolodchikov showed that an infinite number of conformal symmetries exist in two spatial dimensions. These symmetries can be used to constrain the correlation functions of two-dimensional CFTs. The authors exploited these symmetries to solve for the critical exponents of the 2D Ising model, a famous CFT describing a two-dimensional magnet. This particular procedure, called a conformal bootstrap, quickly gained prominence. However, conformal symmetries are much rarer in 3 or more dimensions. Polyakov formulated a bootstrap equation for 3D CFTs, which essentially assumes that one expression of the 4-point correlation function must be equal to the other. In 2008, as the Large Hadron Collider was preparing to search for the Higgs boson, Theorists Riccardo Rattazzi of Switzerland and Vyacheslav Rychkov of Italy and their collaborators investigated whether a conformal field theory, instead of the Higgs, could be responsible for giving it mass. They formulated a bootstrap equation for this hypothetical four-dimensional CFT. Although the equation was too complicated to solve directly, they found a way to place limits on the potential properties of such a theory. They concluded that no such CFT existed, and the LHC confirmed the existence of the Higgs boson in 2012. However, bootstrap techniques have opened up several new possibilities. Their breakthrough involved translating the constraints of the bootstrap equation into a geometric problem. Think of the 4 points of the 4-point correlation function as the corners of a rectangle. The bootstrap equation states that if you perturb a conformal system at the first and second corners and measure the effects at the third and fourth corners, or if you perturb it at 1 and 3 and measure it at 2 and 4, the same correlation function holds in both scenarios. Every function representation contains an infinite series of terms. To determine which terms satisfy this constraint, another consistency condition called unity was invoked, which required that all terms in the equation have positive coefficients. This allowed the terms to be treated as vectors extending from a central point in an infinite number of directions. If a plane can be found in a finite subset of dimensions in which all vectors point to one side, there is an imbalance. Hence, this set of terms cannot be summed to 0 and does not represent a solution to the bootstrap equation. Physicists have developed algorithms to search for such planes, allowing them to connect the space of applicable CFTs with high precision. The simplest version of this procedure produces exclusion graphs, where two curves intersect at a point known as a kink. These graphs exclude CFTs with critical exponents outside the space bounded by the curves. In 2012, researchers applied innovative techniques developed by Riccardo Rattazzi and Vyacheslav Rychkov to determine the critical exponents of the 3D Ising model, a complex conformal field theory, CFT, that shares the universality class at its critical points with real-world systems such as magnets, water, and mixtures of liquids. Nima Arkani Hamed, a physicist at the Institute for Advanced Study, says he is excited about these folds, saying they reveal where important theories lie. He suggests that these findings could indicate a polyhedral structure in the space of allowed conformal field theories, with important theories located at the corners rather than at random locations in the interior. This concept is consistent with Arkani Hamed's 2013 discovery of the amplituhedron, a geometric object that encodes probabilities of particle collision outcomes. The researchers are now extending the bootstrap approach in multiple directions. Simmons-Duffin likened CFTs to road signs in the landscape of quantum field theories. The renormalization group, flows, represent the paths that connect them. By first understanding these road signs, physicists can map the paths and eventually the entire space of the theory. Tom Hartman of Cornell University described the grand goal of the Bootstrap program as mapping the space of quantum field theories. He described CFT graphs as a fuzzy, a priori version of this ultimate map. Discovering the polyhedral structure that represents all possible quantum field theories could unify phenomena as diverse as quark interactions to magnetic properties into a single, inescapable structure. The conformal bootstrap is emerging as a formidable tool in the field of quantum gravity research. In a groundbreaking 1997 paper, Juan Maldacena established a deep mathematical equivalence between conformal field theory, CFT, and the gravitational space-time medium, which has at least one additional spatial dimension. This duality, called the ADS-CFT correspondence, connects the CFT to an anti-de Sitter space, ADS in which the extra dimension emerges from the conformal system like a hologram. ADS space has a distinct fisheye geometry, different from the geometry of our universe's space-time, but gravity works similarly in both environments, producing phenomena such as black holes. Gravity prevents things from escaping. Current theoretical frameworks fail in the case of black holes. In this context, trying to combine quantum theory with Einstein's theory of gravity leads to paradoxes. One of the fundamental questions is how black holes preserve quantum information, even though Einstein's theory predicts their evaporation. If the ADS-CFT correspondence serves as a microscope for theoretical physicists to examine quantum gravity theories, the conformal bootstrap has illuminated that microscope. In 2009, theorists used the bootstrap method to uncover evidence that every CFT that satisfies certain conditions has an approximate dual theory of gravity in ADS space. Researchers have since been working on creating symbolism that will allow critical exponents and other CFT properties to communicate with corresponding properties in the ADS space hologram. This advance could have profound implications for our understanding of the quantum nature of gravity and space-time in our universe. If I have a small black hole, it doesn't matter whether it's in ADS space or not, because it's small compared to the size of the curvature. So if you can solve these conceptual problems in ADS space, the same solution applies to cosmology. Thanks for listening and take care.